Hey Calc BC, welcome to lesson 5.4, the arc length of a planar curve. This is our fourth and final lesson on Unit 5, Advanced Integration Techniques. You can see this is coming from College Board's Unit 8, Applications of Integration, right here, the arc length of a smooth planar curve and distance traveled. Now we have an advantage here because we've already talked about arc length in terms of parametric and polar coordinates. So you already understand the concept of arc length, hopefully. It's kind of like if you take a curve and you flattened it out straight, what would the length of that straight line segment be? It's kind of like measuring the circumference, right? It's as if you took that whole curve and straightened it out. How long would it be? In greater depth, we have this essential knowledge for this lesson. The length of a planar curve defined by a function can be calculated using a definite integral. And that's what we are going to learn today. So let me switch over to the notes. All right, so here are the notes. And as I like to do, I'm going to try to give us a little bit of background on the formula before we really learn it and apply it. So in this section, we will be using a definite integral to define the length of a curve over an interval from A to B. We first need to consider what is meant by the length of a curve. Practically think of fitting a piece of string to the curve to the right. Lift the string and pull it straight, then measure the length of the string with a ruler. This process seems logical, but could be difficult to do with much accuracy, even if the curve was quite simple. We need a precise definition for the length of an arc of a curve in the same spirit as the definitions we developed for area and for volume using integrals. Suppose the curve C is defined by the equation y equals f of x, where f is continuous and a is less than or equal to x is less than or equal to b. To divide the interval from a to b, as you can see here, into n equal subintervals with endpoints x sub 0, x sub 1, x sub 2, and then x sub n is b. And the width of each is delta x. Each point p sub I can be represented by the ordered pair x sub I, y sub I, and when the points are connected, they form an approximation to C. The length L of the curve C is approximately the length of this polygonal path, and the approximation gets better as n increases. So you can see over here, right now we have p sub 0, p sub 1, p sub 2, p sub 3, etc. And you can see if we break this curve into chunks and then add up the length of each line segment that's formed by connecting the dots that we have, we're going to get an approximation for the length of the actual curve. And the more kind of line segments that we split into, the better that approximation is going to be. So this is going to lead us to an integral, but let's first start by just kind of figuring out what are we going to stick inside of this interval where, well, I mean, for each one of these points, you might be able to think, oh, to connect 2 points, we can use the distance formula or the Pythagorean theorem to find the length of a line segment between any 2 points. And you're exactly right, that's what we're going to do. So I want us to think about that the distance formula all the way back from algebra 1 is the square root of x2 minus x1 squared plus y2 minus y1 squared. And that comes from the Pythagorean theorem. And we're going to use a variation of that distance formula, but we're going to make it more calculus-like by changing x to delta x and y to delta y. So our distance is going to be the square root of delta x squared plus delta y squared. And now that's going to give us, like the distance. But we don't want that to be inside of our integral because we've got a delta x and a delta y. That's really no good, right? Because we don't want to have to do this as implicit differentiation. We want to, or integration rather, we would want there to just be x's or just y's, not both inside of here. So let's see if we can kind of break this down a little better using the mean value theorem. So the mean value theorem states that the average slope, which appears at some x value c in any interval, is given as f of b minus f of a over b minus a. And that's just a fancy way of saying that the slope, the average slope between 2 points on a continuous smooth curve is, the slope of the 2 endpoints connected by a line. So let's change this using the same idea as up there. F of b minus f of a. That's a chain into y values, right? This is a y value, this is a y value. So if we're subtracting two y values, it's like y2 minus y1, or we consider it like delta y. B minus a is the difference between two x values, I meant to write. So we consider that delta x. And so we have f prime of, I'm just going to start to call this sum x is equal to delta y over delta x. And then I'm going to multiply the delta x to the other side for our purposes. So we have f prime of x times delta x equals delta y. And that's the variation that we want. I'll show you why in a second. So we have delta y equals f prime of x times delta x. Now, the reason we wanted to solve that for delta y is because it would be really nice if we could replace delta y or substitute something in that had delta x in it instead, and then now this does. So now we're going to use these formulas to write the length of each line segment. So we're going to start with that distance because that really does tell you the length, but we're going to try to simplify this a little bit. So we've got the square root of delta x squared plus delta y squared. And now I'm going to substitute in for delta y. So we have the square root of delta x squared plus f prime of x times delta x squared. And I'm going to factor out a delta x squared from each term. So we really now have square root of delta x squared times, and if I'm factoring out, I'm going to end up with a 1 plus, and over here we're going to have f prime of x squared. And now the square root of delta x squared is just going to be delta x. So then I can take out a delta x and I'm left with the square root of, no parentheses, 1 plus f prime of x squared. And it would be really nice if this squared and this square root could cancel out, but they can't because we have this pesky plus sign in here. So this is like two terms. So we can't just take the square root of one part of that factor. And I'm going to rewrite this one more time with the delta x at the end because that's going to lead us to the integral. Okay, so if you think of the original as a Riemann sum, you might remember summation notation. I'm going to show you this real quick, but you do not need to memorize this. We have the limit as n approaches infinity of the summation of I from 1 to n of the square root of 1 plus f prime of x squared delta x. So that's really the proper notation here that we could use. We want infinite n's so that these points are infinitely close together and we can add all of the distances together. We would never do that by hand, but that leads us to the arc length formula, and this can transition to an integral just like when we did a Riemann sum and changed it into an integral back in the day. We call it L. L is going to be the integral from a to b of the square root of 1 plus f prime of x squared, and our delta x becomes our dx in our integral. All right, so we figured it out. And this can also apply in the context of y. I'll write that down here just so that we know that. I'll just say it could also be from c to d, square root of 1 plus f prime of y squared dy. Okay, so let's apply this to a couple examples. Find the exact arc length of the arc of the semi-cubical parabola y squared equals x cubed between the points 1, 1 and 4, 8. So if I solve this for y, I would get y equals x to the 3 halves. And I'm going to need y prime. So y prime is going to be 3 halves x to the 1 half. So that being said, if I think about my formula for L, the arc length, it is the integral from 1 to 4, the x values, of the square root of 1 plus, it's always 1 plus, and then we do y prime squared dx. Again, that came straight from our formula, right? So our formula had f prime of x squared plus 1 in the square root. So that's what we have there. So let's start to evaluate that then. It did tell us to find the exact length, so we're going to try to do this one by hand. So the square root of 1 plus, if we square this, we're going to end up with 9/4 x. So for this question, I'm going to let u equal 1 plus 9/4 x. du is going to be equal to 9/4 dx. So this is going to have to equal, I'm going to have to introduce a 4/9 so that there's a 9/4 dx. It's not going to be from 1 to 4 anymore, so 1 is going to be 1 plus 9/4 times 1. Okay, so that's going to be 4 plus 9, so that's going to be 13/4. And 1 plus 9/4 times 4 is going to be 1 plus 9. So the upper bound is 10. And now we have the square root of u du, because the 9/4 and the 4/9 make it. So I can just put a du straight in there. And let's see, now we can take the integral. So we have 4/9 times, that's u to the 1/2, so it's going to be u to the 3/2 times 2/3, evaluated from 13/4 to 10. And so now I have 8/27 times, I plug in 10, I get 10 to the 3/2 minus 13/4 to the 3/2. And technically that is a perfectly valid answer, right? We simplified enough that we could just kind of call it a day. But I'm going to go a little bit further, and I'm going to say that 10 to the 3/2 is square root of 10 cubed, so it's going to be 10√10. 13/4 to the 3/2 is going to be what? On top, we'll have 13√13 again. And on the bottom, we have the square root of 4, which is 2, and then cubed is 8. Okay. So then this ends up becoming 80√10/27 minus what, the 8's cancel. So we just get 13√13/27. So if you want to go crazy, there's another valid version of the solution, but either one works. Example 2, arc length. Find an approximate, so this time it's okay for us to use the calculator, approximate length of the curve given by x equals y squared from 0, 0 to 1, 1. So if x equals y squared, it is perfectly fine for us to just do this as a dy integral. So I'm going to leave it as x equals, I'm going to say x prime equals 2y. I'm going to say L equals the integral from 0 to 1. This time I'm doing that because those are the y values here in the ordered pairs. And I'm going to have a square root of 1 plus 2y squared dy. So that's going to become the integral from 0 to 1 of the square root of 1 plus 4y squared. Don't forget to distribute the squared to whatever's inside of those parentheses. And I'm going to stop right there and type that into my calculator. And once I do that, I'm going to round to 3 decimal places and I get 1.479. I'm not going to make you watch me type that in, but I encourage you to try to type that in to either Desmos or your graphical calculator and see if you get the same answer, just to practice typing something like that in, make sure you get the parentheses all correct. Let's try example 3, the arc length of a hyperbola. Again, we're going to be doing approximate arc length this time. We have x, y equals 1. We're going to go from 1, comma 1 to 2, comma 1/2. This time, since it's not obvious, I'm just going to solve for y equals. We'll get y equals 1 over x, and y prime is going to be negative 1 over x squared, or negative x to the negative 2. So my L, my arc length, I am doing a dx this time. So it's going to be from 1 to 2, square root of 1 plus negative 1 over x squared, squared dx, which we might just make it look a little bit nicer before we plug it in. Square root of 1 plus 1 over x to the 4th dx. So now once again, I can type that into my calculator, and I'm going to get 1.132. And to be clear, if we sketched the curve that is on this graph from 1, comma 1 to 2, comma 1/2, the distance on the actual curve, the length of that curve would be 1.132 if we could stretch it out straight. One more question, example 4. Find the arc length function for the curve described by y equals x squared minus 1/8 natural log of x using p0 of 1, comma 1 as the starting point. What on earth is this talking about? Well, this is saying that we want to be able to find a function where we could plug in any x value and it would give us the length from 1 to that x value on the curve. I'll explain as we go, but let's just start off by taking the derivative. So we have y equals x squared minus 1/8 natural log of x. Y prime then is going to be what? 2x minus 1/8 times 1 over x. So it could just be 1 over 8x. So our L this time, I'm going to go from 1 as our starting x value to x. So I'm going from 1 to x. I don't know what x is. I'm just going from 1 to x. And because that's going to be our x this time, I'm going to change the variable of what we plug in to t. So it's going to become 1 plus 2t minus 1 over 8t dt. Okay, so let me just reiterate what we're doing here. We are finding an arc length function if we start at 1, comma 1. So we're starting at the x value of 1. The x is going to be where we end, and no matter what x we plug in here, this function is going to tell us the length of the resulting curve from 1 to that x value along this function. So let's just keep going and see if we can solve this by hand. So we have the integral from 1 to x of the, oh, you know what? I forgot to put that was squared. Let's not forget that. That's important. It's going to be the square root of, I'm going to actually, do this FOIL. So we've got 1 plus 2t times 2t is going to be 4t squared. We do outer and inner. So the outer is going to be what? 2t times negative 1 over 8t. That'll be negative 1/4. And we've got a negative 1/4 as the outer and a negative 1/4 as the inner. So that's going to be minus 1/2 in here. And then as the last term, it's going to be negative 1 over 8t times negative 1 over 8t. So that's going to be positive 1 over 64t squared dt. We've got 1 minus 1/2. So I'm going to subtract that just to simplify here. And let's put this stuff in a logical order. So we'll have 4t squared plus 1/2 plus 1 over 64t squared. All right, so this is where it might not be super obvious what to do next, but this actually can be refactored. So we have a perfect square term here. This is going to be 2t. And we have a perfect square term here. This is going to be 1 over 8t. And if we have that as our two terms in our binomial, the center is actually going to become positive 1/2. So let me show you what I mean. I know this is a little bit complicated, and you won't have to do something quite this demanding on a test, so don't worry too much about it. But it is good practice to see this, and there might be something similar on practice worksheets. So if we switch this to a plus, right? Let's try foiling this, and we're going to get this. We have 2t times 2t is 4t squared. 2t times 1 over 8t is going to be 1/4 plus 1/4 is 1/2. That's for the outer and the inner of the foil. And then the L, the last, is 1 over 8t times 1 over 8t, which is, again, that 1 over 64t squared. So the whole reason we wanted to do that is because now the square and the square root cancel out. So we end up with 1 to x of 2t plus 1 over 8t dt, which is much simpler to integrate. So we end up with what? T squared plus 1/8 natural log of t. Yep, that's what that's going to become. And we're going to evaluate that from 1 to x. So we end up with x squared plus 1/8 natural log of x minus 1 squared plus 1/8 natural log of 1. And natural log of 1 means e to what power equals 1. That's a 0, so that just goes away. And so our final answer is going to be x squared plus 1/8 natural log of x minus 1. All right. So that was an example of how this could get a little bit more difficult. And for example, what this now means, let me just kind of finish up this problem quick. If we start at 1, 1, let's say that we plugged in 4 for x, whatever we get, so we get 4 squared plus 1/8 of natural log of 4 minus 1. Okay, so that value is the length of the curve from an x value of 1 to an x value of 4 on this curve. So we kind of rigged our integral, figured out a general solution for the length of the curve from 1 to x. It's pretty interesting if you ask me. So that's how we did that. Again, that's a little bit more complicated. These first 3 questions are much more commonly what you will see about arc length. Really, you just need to make sure that you know how to apply that formula. All right, so that is it. Thank you so much for watching. Have a great day.